All right, strap in, everyone. Today, we're tackling a paper with a title that sounds like, well, it sounds pretty intimidating, honestly. Parity-time, symmetric, holographic principle. But don't worry.
We're going to break it all down.
Exactly. We'll make sure you don't need a physics PhD to keep up.
That's right. What we're really looking at here is a new way to solve some really challenging physics problems, the kind that you would normally need massive computing power to even begin to address. The crazy part is they're doing it using just one qubit.
Okay, color me intrigued. So this deep dive is all based on a research article from the journal Entropy, published in November 2023. Basically, they're saying you can use the way a qubit changes over time to actually solve problems about things happening in space.
Yeah?
It's like that qubit is a tiny little hologram holding the information for a much larger system.
Exactly. Think of it like this. You want to study how a particle, say, scatters off an atom. Traditionally, you'd need a supercomputer to simulate all those crazy interactions. But this new approach says you can get that same information just by watching a single qubit evolve over time.
Hold on. So instead of crunching numbers on a supercomputer, we can just watch a qubit do its thing, and it'll basically unlock the secrets of the universe.
Pretty much, yeah. It's pretty wild.
That's amazing.
It is. And it gets even more mind-boggling because they use some pretty unusual physics to pull it off. Things like PT symmetry. But don't worry, we're going to explain it all. No prior knowledge needed here.
Awesome. I am ready to be blown away. So let's start simple. How can a single qubit even begin to represent something as complex as a particle moving through space? I mean, how is that even possible?
Well, let's start with a really simple scenario. A massless particle moving in just one dimension.
Okay.
Think of it like a bead sliding along a wire. Its energy and momentum are directly related, like a straight line on a graph.
Okay, got it. So simple movement, straight line.
Now, believe it or not, that movement can be represented perfectly by a qubit.
Really?
Yeah. We can even visualize it using something called the Bloch sphere.
Okay.
Each point on the sphere corresponds to a different state of the qubit, reflecting how that particle is moving.
So by changing the qubit state, we're basically controlling the particle's motion.
Exactly.
Wow.
But of course, things get a little more interesting when we introduce mass into the equation.
Right, because nothing in physics can stay simple for too long.
No, absolutely not. When our particle gains mass, it changes the relationship between its energy and its momentum.
Okay.
Instead of that straight line on our graph, we get two curves that almost touch, but they never actually cross. We call this an avoided crossing.
Okay, an avoided crossing. I think I need a visual for this one.
Imagine two roads heading straight for each other.
Okay.
They're about to intersect. But then at the last moment, they both swerve away, narrowly avoiding a collision.
Okay. Yeah.
That's kind of what's happening with the energy levels of our particle when we add mass.
Ah, I see. Okay, that makes sense. So how does this mass-induced swerve, this avoided crossing, show up in our qubit picture on the Bloch sphere?
Well, now the states that represent our particle at rest, so zero momentum, they lie along the x-axis of the Bloch sphere.
Okay.
So by manipulating the qubit state along that axis, we can essentially simulate the particle gaining or losing mass.
Very cool. Okay, I'm following so far. We've got our qubit standing in for a particle. It can even account for the particle's mass. This is where it gets really weird, though, right? This time-space swap you mentioned earlier.
Right. The researchers basically just swap the roles of time and space in the mathematical description of the system.
So they swap time and space. I'm going to let that sink in for a minute. That's a pretty wild idea.
It is. It's a pretty simple switch, too, but it leads to this mathematical framework called a non-Hermitian Hamiltonian. It might sound a little scary, but essentially describes systems that can lose or gain energy, like the ones we actually find in the real world, where there's always some interaction with the environment.
Okay, so they're bringing a little bit more of that real-world messiness into the model. But how does this time-space swap actually connect to PT symmetry? I know you mentioned that earlier.
Right. That's a great question. PT symmetry stands for parity-time symmetry.
Okay.
Imagine taking a system and flipping all of its spatial coordinates. So it's like you're looking in a mirror.
Okay.
That's parity. Then imagine reversing time, like rewinding a movie.
Got it.
That's time reversal.
Mm-hmm.
A system with PT symmetry would look the same after both of those operations.
So it's like a mirror image that also runs backward in time.
Exactly. And what the researchers found is that by tuning this key energy parameter in their model, they can actually switch between regions where this PT symmetry is either broken or unbroken. And it's separated by a point that they call an exceptional point. They actually depict all this beautifully in figure 2 of their paper.
Okay, so we've kind of laid the groundwork for this qubit hologram idea. We've got this mind-bending PT symmetry thrown into the mix. But how does it actually play out in practice? Give me an example of what this qubit can actually simulate.
Okay, let's look at their first example. Simulating the scattering of a neutron off of an atomic nucleus.
Okay.
Picture a neutron, like a tiny billiard ball, bouncing off a much larger nucleus.
Classic scattering problem. Got it. So how does our qubit come into play here?
Instead of using complex calculations to track the neutron's trajectory, they use a single qubit.
Okay.
They just watch how its state changes over time. And here's the kicker.
Okay.
That time evolution of the qubit directly corresponds to the spatial solution of that scattering problem.
Wait, so you're telling me we can use a single qubit to predict how a neutron is going to scatter? That could save researchers a lot of time and computing power.
Exactly. And to prove it works, they actually compare their qubit-based simulation to actual experimental data.
What?
In Figure 3 of the paper, they show how the potential of that nucleus and the complex scattering wave function are beautifully captured by the simple evolution of that qubit.
That is seriously impressive. But I know they didn't stop there, right? Tell me about the second example with something called a Majorana zero mode.
Right, this example takes us into the realm of topological physics, which deals with properties that stay stable even when a system undergoes continuous deformations. A Majorana zero mode is a special kind of bound state. A particle gets trapped in a specific region.
Okay.
And it's topologically protected, meaning it's really robust against disturbances. They're pretty elusive, have potential applications in quantum computing.
Seems pretty exotic. So how on earth do they simulate this elusive Majorana zero mode using just a single qubit?
Well, they cleverly model a changing mass parameter in their system. It causes this topological phase transition. Think of it like tweaking a knob that fundamentally alters the system's properties. And guess what?
What?
The emergence of that Majorana bound state is revealed through the time evolution of our trustee qubit.
No way. And they show all this in Figure 4, right?
Yes. Figure 4 beautifully illustrates how the qubit's time evolution reveals both the bound state energy and its wave function, which, by the way, decays exponentially away from the bound state.
Yeah.
And this all ties back to that concept of PT symmetry we were talking about.
Okay.
The exceptional points where the system switches between broken and unbroken PT symmetry, they actually correspond to what we call the classical turning points,
Yeah.
where the particle's motion changes from oscillatory to exponential decay.
So not only can they simulate this incredibly complex condensed matter system using minimal quantum resources, but the PT symmetry is giving us actual insights into the underlying physics. It's blowing my mind.
It is a very elegant approach, incredibly powerful. And to make things even more exciting, the authors suggest that this whole qubit hologram concept can be extended to even higher dimensional systems, like a 3D Dirac particle, which is a more realistic representation of particles like electrons.
Okay, so we've got a qubit acting like a hologram representing complex systems. We've got mind-bending PT symmetry at play. And now we're talking about scaling it up to higher dimensions. I mean, where does this research even lead? What are the implications of all of this?
That's a great question, and it's exactly what we're going to be diving into in part 2 of our deep dive.
Stay tuned. Welcome back, everyone. Man, my head is still spinning from that time-space swap and the idea of a single qubit acting like a hologram.
Pretty amazing stuff, right?
Seriously. But I feel like we've only just scratched the surface of what this qubit hologram thing can actually do.
Yeah, there's a lot to unpack here.
So we saw how they can simulate things like neutron scattering and even those exotic Majorana zero modes, but like, what other kind of physics could this method unlock?
I mean, the possibilities are really vast.
Yeah.
Imagine simulating the behavior of, like, complex molecules to design new drugs or materials. Or, maybe even delving into the mysteries of high-energy physics, simulating the dynamics of black holes, maybe. Systems that were previously, like, totally intractable because they're just so complex, could suddenly become accessible.
Now we're talking. Okay, but hold on a sec. Didn't the authors mention that this method could be scaled up to higher dimensions, like a 3D Dirac particle?
Yeah, right. So far, we've been focusing on mostly 1D examples.
Yeah.
Just for simplicity.
Right.
But in the real world, particles move in 3 dimensions, obviously.
Vectors.
So what's really cool is that this qubit hologram idea, it can still be applied.
So how does that work? Do we need, like, multiple qubits to represent all three dimensions?
No, not necessarily. The authors actually show how you can still just use one qubit.
Wow.
But its time evolution, it just gets even richer,
Okay.
encoding information about all three spatial dimensions at the same time.
So it's like upgrading from a flat photograph to a 3D hologram.
Exactly.
That's awesome. Okay, but there have to be some limitations, right? I mean, no method is perfect.
You're absolutely right. One key requirement here is that the system has to possess what we call parity symmetry, meaning it looks the same if you flip all the spatial coordinates.
Okay.
Not every system has that property. So that does kind of narrow down the range of problems that we can tackle directly with this method.
Okay, so that's one constraint. What other challenges do you see with this method?
Well, the research is mainly focused on static properties,
Mm-hmm.
things like the energy levels of a system or the shape of its wave function. Simulate like dynamic processes where things are changing over time. That might require some further development of the method.
That makes sense. And I mean, of course, we can't ignore the practical challenges of actually implementing this on real-world quantum computers. Noise and decoherence, those are still formidable foes, right?
Absolutely. Noise and decoherence, they're major hurdles in quantum computing in general. But the authors did touch on the idea of using what we call open quantum systems in their approach.
Oh, okay.
Open quantum systems, they naturally interact with their environment.
Right.
So this could actually be a way to incorporate noise and decoherence directly into those simulations.
So instead of seeing noise as like the enemy, we could actually use it to make our simulations even more realistic.
Yeah.
That's a pretty cool idea.
Yeah, it's a really interesting idea. And it highlights a broader trend in quantum computing,
Yeah.
moving away from this ideal of perfectly isolated qubits and actually embracing the messiness of the real world.
Right. Okay. So there are definitely challenges ahead. But I mean, the potential of this qubit hologram approach seems undeniable. What stands out to you as like the most significant takeaway from this research?
I think for me, it's the elegance of the idea. Using the time evolution of a single qubit to encode all the spatial properties of these complex systems is like, it's just breathtakingly beautiful. It really speaks to the power of abstract thinking and how different areas of physics can be interconnected in really unexpected ways.
I totally agree. It's like finding this secret passage that connects all these seemingly different realms of knowledge.
Right.
And who knows what other, I don't know, wonders might lie beyond that passage.
Exactly.
Okay, so speaking of the future, what are some of the, I don't know, key questions that still need to be addressed? Like, what are the next steps for researchers working in this field?
Well, one pressing question is, how far can we actually push this method?
Mhm.
Can we simulate, systems with even higher dimensions or with even more complex interactions?
Yeah.
And what are the fundamental limits of this approach? A single qubit can only encode so much information.
Right. At some point, we're going to hit a wall.
Yeah.
What about the practical challenges of implementation? We talked about noise and decoherence, but there's also the question of, like, finding the most efficient ways to actually encode and decode information using this qubit hologram. It's almost like developing a new language for quantum simulation.
Exactly.
Yeah.
Yeah, there's a lot of work to be done, both theoretically and in terms of developing new experimental techniques. But I have to say, I'm really excited about the future of this research. I mean, this paper has really sparked my imagination.
Yeah, I can hear the enthusiasm in your voice.
Yeah.
It's not every day that we encounter such a novel and potentially transformative idea.
You're right. This is one of those moments where you realize we're really just beginning to glimpse the true potential of quantum mechanics.
Well said. And with that, we've come to the end of part 2 of our deep dive. But we're not done yet. In part 3, we're going to step back and kind of explore some of the philosophical implications of this research, particularly its connection to the mind-boggling holographic principle in cosmology. So stay tuned.
Welcome back to the deep dive. We've gone through some, well, pretty wild physics in this episode, from swapping time and space to the idea that a single qubit could act as a hologram for these crazy complex systems.
Yeah, it's been a wild ride for
It
sure.
really has. But now we're going to do what we promised. We're going to take a step back and ponder some of the bigger, philosophical questions that this research kind of brings up.
Right.
Okay, so I am ready to get philosophical. What kind of deep thoughts has this paper sparked for you? Well, I think, the idea that a single qubit can encode all this information about a much larger system, that's a really intriguing idea. It reminds me of another pretty mind-boggling concept.
Yeah.
The holographic principle in cosmology.
Oh, yeah, the holographic principle. I've heard of that. It's like the idea that our entire 3D universe could just be a holographic projection of information that's encoded on a 2D surface, kind of like a cosmic movie projected from this distant screen.
Exactly. Yeah, and while this research isn't directly related to cosmology, it does kind of hint at a similar idea, this information duality, where something seemingly simple, like a qubit evolving in time, it can actually hold the key to understanding something much more complex, something that's extended in space.
So are you saying that, like, our everyday reality, the world we experience around us, could actually be a kind of hologram
Right.
with all its information, like encoded somewhere in the quantum realm?
It's a fascinating thought, isn't it? This research doesn't actually prove that, obviously, but it does kind of encourage us to think differently about the relationship between information and physical reality. It makes you wonder if what we perceive as real is really just one level of a much, much deeper, more fundamental reality that's encoded in this, language of quantum information.
Wow, that's a deep rabbit hole to go down.
It is.
Makes you wonder if we're just like scratching the surface of what's really going on, at the most fundamental level.
Right.
Okay, well, I love how this paper, this technical paper about qubits and simulations has led us to these big questions about the nature of existence, about reality.
Yeah, it's a really cool example of how science, at its core, it's driven by curiosity, by this desire to understand the universe. And sometimes those pursuits can lead to these questions we never even thought to ask.
Definitely. All right, so as we wrap up this deep dive, what are some of the, key takeaways you hope our listeners will think about?
You know, I think the biggest takeaway here is that we should never underestimate the power of a new perspective. This research shows us that even these seemingly simple systems, like a single qubit, can actually hold the key to unlocking these profound insights about the universe.
Yeah, totally agree. It's a good reminder that the universe is full of surprises and that the quest for knowledge, well, it's an endless journey.
It really is. And who knows what other, amazing discoveries are waiting for us in the future.
Sure.
Maybe we'll even find, like, deeper connections between quantum mechanics, information theory, and the fabric of space-time itself.
Well, I can't wait to find out. And on that note, we've reached the end of our deep dive into the parity-time symmetric holographic principle.
It's been a pleasure exploring this fascinating research with you all.
If you want to learn more, we encourage you to check out the full paper yourself. You can find it at Song X, Merch, K, parity-time symmetric holographic principle, Entropy 2023, 25, 1523.
And just remember, the universe is a vast and mysterious place, always ready for us to explore it.
Until next time, keep questioning, keep learning, and keep diving deep.